Today we have a talk of Georgii Riabov devoted to stochastic flows of mappings. Please, Georgii.
In my talk, I will propose a new approach to constructing measurable stochastic flows of mappings. These are our joint results with Olivier Raymond. I will consider stochastic flows in a locally compact separable metric space. And let me recall the notion of consistent sequence of coalescing Feller transition functions. So this is a sequence of transition functions such that Pn is a Feller transition function on m to the power n. The consistency means that Pn defines Pk when k is less than m, and coalescing property means that if we have let's say a Markov process with a transition function P2 that starts from points xx, then both components of this process are equal for all t bigger than 0. Okay. With such a sequence, one can associate a measurable stochastic flow of mappings in the following sense. So let F be the space of all measurable mappings of M, equipped with a cylindrical sigma field. Then a theorem of Lejeune and Raymond states that there exists a family.
Okay, you can continue.
There exists a family of random elements in the space F that are defined on some probability space such that this family is measurable in st, x, and omega for any random element x in m to the power n, which is independent from psi st, and for any continuous function f that vanish at infinity, expectation of f of psi of x is equal to expectation of Pn t minus sf of x. So we can fix x, take expectation, and then take expectation one more time. Psi ss is the identity mapping on M, and for all s less than t less than u, and for all x, the value psi su of x is almost surely equal to the composition of psi st of x and psi tu. When we have times t1 less t2 less than tn, then mappings psi are independent, and we have some kind of continuity in probability in time and in space.
Georgii, and exceptional set in the second item.
Here,
so does it depend on T, S, and U? And
yes, it depends on S, T, U, and X.
Thanks.
So let us note that if we have a family psi prime that satisfies this condition and also almost surely equals to psi, then it is also a measurable stochastic flow of mappings. And we will call it a measurable modification of psi. Still, since stochastic flows exist, it is not clear what is the dependence of these flows, let's say in T. In fact, if we fix S and X, then we will get a failure process. In particular, it has a Cadillac modification, but it is not obvious if we can find such measurable modification that all functions psi prime s omega x are Cadillac. Because for each s and x, we will change this process on a set that depends on s and x. And in the end, we can get the process psi prime that is not measurable in s, t, x, and omega. And also, it is natural to ask for the strong flow property in the sense that for all s less t less u, and for all omega, the composition of the mapping psi st and the mapping psi tu is equal to psi su. Actually, it is known that for any consistent sequence of Markov transition functions, one can construct the stochastic flow for which the strong flow property holds. But these flows are not measurable in S, in T, and in X. Okay, I will consider only flows with continuous trajectories. Hence, I will assume that the transition functions P1 satisfy this condition. And by a strong measurable continuous stochastic flow of mappings, I will understand a measurable stochastic flow of mappings with all continuous trajectories psi sx, and that satisfy the strong flow property. I mentioned that existence of strong measurable continuous modifications is known for example, stochastic flows of solutions to regular stochastic differential equations. Also, in my previous work, I showed existence of such modifications for some instantaneously coalescing stochastic flows on the real line. Also, existence of such modifications is known for some measure value to flows related to the Brownian web.
What does it mean related to the Brownian web?
It means that in the Brownian web, we have independent Brownian motions that meet, and they can coalesce or not. And these measure-valued flows, they allow to to split like points.
Maybe the flow itself does not allow this because you have the continuous trajectories, but you just can choose.
So
range.
the Brownian web is not a flow.
Yes, exactly. Yeah.
Yes.
So choosing the right direction in these double points, you can construct some flow. Yeah.
Yes, and also you can like give some probability p and 1 minus p to choose like how to split, and then you get a measure of valid flow.
But not to split, to choose a way. Yes, because in your construction you mentioned that one particle have a trajectory which is continuous. Yes, so
Yes.
So the particle cannot split onto two particles.
Yes, yes, yes.
So just not to split, but choose a way. Yeah, and they produce a right right mechanism to do this choice. Yes.
Yes, but for measure the valued functions.
Oh, for measure value. Okay, okay.
Yes.
So I'm sorry, I just not think about measure value flow. Okay, that's another story.
Now, to explain my approach, let me recall some notions that we had already. So I will consider the space of path. This is the space of all continuous functions in M that start at all times S. And it is a complete separable metric space. We can define a metric in such a way that convergence in this metric means the convergence of initial times and uniform convergence of functions.
Locally uniform.
Yes, yes.
And locally uniform on the intersection of domains, because initial point may be different.
Yes, so if we have like one function f and one function g, we just extend them, and convergence in this space means that initial times converge.
Okay, I see.
And this
This extended function
yes.
converge locally uniform.
Yes.
Thanks.
Yes. Okay, so when we have a sequence of paths, we will call it a skeleton if once two functions from this sequence coincide at some time s, they coincide at all times after s. Also, the set of initial times and initial points is dense, and for every compact L in the product of R and M, we consider the set of restrictions of all functions phi n after they have been in the set L. And this set must be relatively compact in the space of path. So by S of M, I denote the space of all skeletons. And we had the following result, that there is a measurable mapping that for every points S, X, and every skeleton F sends to some function and this function starts from x at time s, and this mapping preserves the skeleton in the following sense. So if we consider the mapping that starts from the point which is on the skeleton, then it continues the trajectory of the skeleton. And moreover, every such function is a limit point of the trajectories of the skeleton, limit point in x. Then we can define the family of mappings theta st of phi and x, and get a family of mappings of M, which is a measurable function in S, T, X, and phi. Now, the idea is to take a stochastic flow, to choose a skeleton from this stochastic flow, and substitute it here. So by psi0, I will denote a measurable stochastic flow of mappings that corresponds to our sequence of transition functions. We choose some dense set in R times M, and by phi of n, I denote a continuous modification of trajectory psi0, Sn of xm. And I will assume that for any compact L, this set is almost surely relatively compact. So this means that the sequence phi is almost surely a skeleton. Now, we also showed that the mapping theta can be defined in such a way that if we put here big phi, yes, then we will get a measurable continuous modification of psi0. Moreover, this modification is such that for any stopping time, it almost surely has the flow property at this time.
All these are assumptions. Yeah.
Yes, under this. Yes.
So if we have this, then you can prove this.
Yes, yes, yes.
Mhm.
But this modification theta may not be a strong measurable continuous modification. And this is because of existence of so-called bifurcation points. So now I will denote, I will define what it is. Now let us fix some skeleton phi and look at the mapping theta. So by kst epsilon x, I denote the closure of all functions theta. This is S. this is t, this is x. I denote the closure of all functions theta from s to t such that at time s they were in the epsilon in the neighborhood of x. And by our assumptions, it is a non-empty compact set. So we consider the intersection of all these sets k, st, epsilon x. And hence we get a non-empty compact set of continuous functions on st. And this set contains a function theta s of x.
Georgii, so this is a random set.
Now I fix phi.
Mhm.
So not. So this set depends on phi, and
Okay.
this also depends on phi.
But it can contain something else, not only
Yes,
this.
yes. And by nu st of x, I denote the number of elements in K, and by tau, I denote the infimum of times that nu is bigger than 2.
But can it happen that nu is infinity, or
Yes,
it is uncountable?
yes.
Do you have such examples?
Georgii, maybe you can start with examples with countable or just infinite number, just to understand what happens.
Georgii?
Yes, well, I didn't construct such examples, but it can be, I think, infinite.
So you just think that it can be.
I think it can be, yes.
What is the reason?
Well, so I don't have a concrete example when it is infinite, but I'm interested only at times when it is when nu is bigger than 1.
Okay, and can you just draw a picture when it is it is greater than 1?
But
Yes,
we have it already in Brownian web, I think.
yes,
Yeah?
it is the example of Arate flow. Yes.
But it is a random time, yeah, when it happens.
Yes.
Mm-hmm.
But for some phi, we will have times when tau is bigger than 1.
Mm-hmm. Okay. And
also I will show an example at the end when tau is bigger.
Yes, as far as I remember, in Arate web, they proved that there are only these double points. There are no, for example, triple point and so on.
Yes, so there are no triple points, yes.
Yes, and this is due to the order. Mm-hmm.
There is also a result by Georgii Kaspi.
Mm-hmm.
They have a stochastic flow of skew Brownian motions where they proved that there are points of multiplicity 3.
Mm-hmm. Mm-hmm.
But we are interested only in the case when we have
such point or not?
What?
When we have such a double point or not? Yes.
Yes. So I denote the set of bifurcation points as the points where tau Sx is equal to S. So like when immediately after time S, we have at least two limit points. Okay. The main idea is to modify trajectories of theta when they hit this set B. But this set B can be of a complicated structure. It can be, for example, dense. And to avoid these problems, let us assume that F is a closed set that contains B.
By the way, can we just prove that B is measurable or something? So can
we can
just
prove that it is a
set
measurable
something?
set, but it is hard to work with heating times of B. Because now I will work with heating times.
Yes, yes, it is reasonable, but it is interesting to see the structure of B itself. So I asked it. This was the reason why I asked it, for measurability or some other properties.
It can be proved that B is a measurable set.
Okay.
Okay, so now let us assume that there is some closed set that contains B. We can always find such a set because we can always take
for example,
R times M.
multiply M, yes.
Yes. And for such set, let us define a sequence of heating times, heating points. Basically, sigma Sx of k is the first time after sigma Sx k minus 1 when we hit set F. And Z is the heating point. So if sigma is infinity, we can just put Z equal to X.
So let me ask you again. Sigma k, sigma, for example, sigma first is the first heating time of F, yes?
Yes.
Then what is sigma 2?
Is the first time after sigma 1 when we hit F.
But it can
But
happen
maybe
that,
it can be equal to sigma 1.
Oh, okay. So it can happen that they are all equal, yeah?
Yes, yes.
Okay.
So this sequence is a non-decreasing sequence of numbers, maybe infinity. If some sigma is equal to infinity, then all future sigmas are also equal to infinity, and that is equal to X. And by K as X, I will denote the first time, the first index K, such that sigma K is equal to sigma K plus 1. So again, maybe K6 is in infinity, and maybe not. Now, after this index K, all sigmas are equal, all Z are equal, and the mappings sigma and Z, they are measurable functions of S, X, and the skeleton phi. And actually, it is not hard to show. Okay, now after this definition, sorry.
No.
After this definition, let us define the family of mappings psi. Let's say that this is our set F. The mapping psi is defined as follows. So we start from theta s x. Then we hit F. Let's say that this is sigma sx of 0. This is sigma sx1. After that, we define psi to be theta theta of sigma sx of 1 from z sx of 1. Then we hit, let's say, F at some time sigma sx2, and we define psi to be theta sigma sx2 of z sx2. But it can happen that, let's say, sigma sx3 equals to sigma sx4. So here k is equal to 3. And after this time, we just define psi as theta sigma sx of ksx.
And what is F now?
F is some closed set. In this example, F is just R times 0.
Okay, thanks.
But what if F really equal F R multiplied by M?
Then psi is theta.
So we have no improvements, yes?
Yes, yes.
Yes.
So if k is less than ksx, then all times times sigma sx are finite. Z is equal to psi at time sigma sx of k, and sigma sxk plus 1 is the first time after sigma sxk when psi hits F. If k is finite, then the function psi is a continuous function of t, and it is defined for all t bigger than s. Okay, and now I will give a sufficient condition when psi has a strong flow property. When psi su is equal to psi tu composition psi st. Assume that for all s and x, these indices k are finite, and if k is 0 in the sense that sigma sx1 is equal to s, then for any t bigger than s, the mapping theta coincides with the mapping from the skeleton. Then, okay, so then we have that psi is a continuous function defined on S infinity. It starts from X. It preserves the skeleton, and it satisfies the strong flow property. In fact, continuity we have by construction. The preservation of the skeleton we have because of theta. So we only need to check this one. Now let's consider such sets. So the set SD is the set of all pairs Sx where k is equal to d. Now the union of all SD is equal to R times M. Okay, and let's prove by induction. So if d is equal to 0, then just we have that psi is equal to theta. But
Maybe
by
1,
our
not 0, but 1.
no,
We have at least one element in those set, yes? Yes.
no.
D, what is D? D again is the number of
Sx is
elements.
equal to 0. It means that the first time after S when we hit F is equal to S.
I see.
But then by our assumption,
Mhm.
for any t bigger than S, we have a
Mhm.
function from the skeleton
I
that
see.
coincides with psi.
Mhm.
And since theta preserves the skeleton, we get what we need. And now assume that the statement is proved for d minus 1. Let k Sx be equal to d. And let us consider the time t between S and the first hitting time. Here y is psi st of x. It is equal to theta st of x. And it is not an element of f. Then ty is not a bifurcation point. But then we actually showed it before that at this point up to hitting f, theta ty coincides with theta sx. Because this is an element of, let's say, kty, and this is also an element of kty. But up to hitting f, kty has only one element. So we can conclude that hitting times sigma sx1 and sigma ty1 are equal, and psi sx and psi ty coincide up to the hitting time. But if if we hit F, then actually all this sigma Sx and ZSX, they coincide with sigma Ty and ZTy. After hitting time sigma Sx1, at this time we just get that the heating time and heating point belongs to SD minus 1.
Why?
Because sigma RW of J is just equal to sigma Ty of J plus 1.
So it's still unclear why we just move. Oh, okay, can you draw a picture?
Yeah, so we started, let's say, here. This is, let's say, Ty. This is RW. So the next time when function psi is in the set F, it's just one more after Ty hits F.
Yes.
And so on.
So okay, yeah, I see. Okay.
So this proves the theorem, and as a consequence, we can reformulate it for stochastic flows. So assume that phi is a skeleton constructed from the flow psi 0. Assume that some closed set F contains the set of bifurcation points of theta with probability 1. Then we can define sigma, and they will be stopping times. We can define Z, K, and psi.
Let me ask you the following. As far as I remember, when you define skeleton and define this theta, you said that one can prove the following lemma, that there exists a measurable mapping
Yes.
from the space of all skeletons. Yes?
Yes. Yes.
So now when you say random skeleton, you just mean the random elements in the space of skeletons.
Yes. Yes.
And then we can apply this theta and get again a random something. Yeah.
Yes. Yes.
Okay. Thank you.
Georgi, could you please explain about stopping times? F is so you have a flow,
Yes.
a stochastic process. You have some filtration, and
Yes. So
these closed set.
the filtration that I consider is a theta, let's say, of T. It is the filtration that is generated by theta UV, where U less V less T.
Okay, but this closed set F that contains bifurcation points.
It is not random.
And bifurcation.
The set of bifurcation points is random, but we assume that there is one closed set that contains all sets of bifurcation points.
Okay. So if F is not.
Then sigma will be stopping times. Yes.
Stopping.
Yes.
And do you assume that filtration is continuous from the right? So do you add some null sets?
Well, all that I need is the strong Markov property of finite point motions.
Mhm.
So we consider stopping times with respect to filtration a theta t plus.
Yeah, so this was my question. Thanks.
Now assume that almost surely for all s and x, k is finite, and if k is 0, then for any t bigger than s, for some, this must be Sn less or equal to t, the function theta coincides with the function from the skeleton. Then we have that psi is a strong measurable continuous modification of the flow. As an example, we can consider instantaneously coalescing flows. These flows are such that with probability 1, for all s strictly less than t, the set of the set of points of the skeleton at time t that started before time s is locally finite. In this case, we just take f to be r times m, psi is theta, and this is a strong measurable continuous modification of psi 0. Before we had an example that there exists a strong measurable continuous stochastic flow and metric graph whose finite point motions are coalescing Walsh-Brownian motions independent before meeting. The
Georgi,
second, yes.
and these Walsh-Brownian motions, they move independently before they hit each other.
And yes, and after hitting, they coalesce.
Yeah, so theoretically they may move parallelly in parallel. But okay, so it's like a Aratia flow, but Walsh-Brownian motion.
It's like a Aratia flow on a graph.
Thanks.
The second example is Tanaka SD. We actually also had it before, but now let's apply the result to this example. So we define transition functions Pn as follows. So x1, xn solves such problem. So this is each xi is a solution of Tanaka SD with initial point xi, the same Brownian motion B, and when two solutions meet, they must coalesce. So it is well known that the weak solution of this problem is unique. So we define transition function Pn as the distribution of x1, xn. Then we get a consistent sequence of coalescing failure transition functions. We can construct a measurable stochastic flow. We can choose phi n, and it will be almost surely a skeleton. Because all functions phi n, they have the same modulus of continuity. So all problems we have at 0, so we will let f to be r times 0. And then we can define all this sigma, z, and k.
Georgi, so please return a little bit back. So do you apply here the previous theorem?
Not yet.
Because in the previous theorem, you say that the number of points is locally finite. So could you please?
No. So this was one example, and this is second example.
Okay, another example.
Yes.
Thanks.
Yes. And actually, almost surely, for all s and x, k cannot be bigger than 2. And if k is 0, then we can always find the function from the skeleton that coincides with theta after time t. So to show that k cannot be bigger than 2, let us know that if theta is separated from 0, then the absolute value of theta is equal to absolute value of, let's say, theta as a plus the increment of the Brownian motion. Now, if k is bigger than 2, then we have our stopping times, sigma sx0, which is s, sigma sx1, 2, and 3. On these intervals, theta is not 0, and these values z as x1, z as x2 are equal to 0. So it follows that at times sigma sx1 and sigma sx2, the Brownian motion has local minima. And these local minima, they are achieved at the same level. But it is known that the probability that the Brownian motion has two local extrema at the same level is 0. Okay. Then if k is equal to 0, then x is equal to 0. And here we have a function theta that starts from 0 at time s. So if this point was already the value of the skeleton, then the function will be equal to the function from the skeleton. If not, then theta is a limit point of functions from the skeleton. In particular, well, let us assume that we have some functions that approach it from above. Again, if all these functions are bigger than 0, then it follows again that S is the minimum of B from S to T. But since sigma sx1 is equal to s, we can find two values alpha and beta where theta is equal to 0. And it follows that both alpha and beta are local extrema of B at the same level. Okay, we know that this cannot happen. So one of the functions phi hits 0, but then all others will also hit 0.
Mhm.
So we have that after this hitting time r, theta is equal to a function from the skeleton. So this proves that there exists a strong measurable continuous modification of the Tanaka flow. And one more example is the example with the skew Brownian motion. Okay, we have a Harrison-Shep SDE. So here B is a Brownian motion, L is the symmetric local time at 0 of x, beta is from -1 to 1. It is known that we have a unique strong solution of this equation. So we define transition functions as follows. Xi is a solution to the Harrison-Shep SDE with initial points xi. And Pn of t is just the distribution of x of t.
So with the same Brownian.
With the same Brownian motion.
The same Brownian.
Again, we have a consistent sequence of coalescing failure transition functions. We can construct a stochastic flow. We can choose functions phi n. And again, actually, all functions phi, they share the same modulus of continuity. So it is almost sure a skeleton, and we can define a modification.
Why do they have the same modulus of continuity?
Because of Georgii and Kaspi.
So they have.
They have, as I remember, they have a modulus of continuity 4 times modulus of continuity of B.
Okay, maybe.
Because outside 0, they just coincide with B.
Yes.
And again, all problems we can have only at 0, so we let f to be r times 0. Now, let's consider the case when beta is from 0 to 1. Again, with probability 1, for all s and x, k is not bigger than 2. And if k is 0, then for all t bigger than s, function theta s coincides with with the function from the skeleton.
And why all of this k less than 2? So this
I
is
will,
the
I will
result.
explain. I will
Okay.
explain. So if theta is not 0 on some interval, then it is just equal to theta sa plus the increment of the Brownian motion. If k is bigger than 2, again, we have 4 hitting times, sigma 0, 1, 2, 3. And functions theta sigma of z are not 0 between these hitting times.
but may so is it so KS is a number of distinct points, yeah, is it correct?
K,
So yes.
KS is yes. So we have like sigma S0, then we have sigma S1, sigma S2, and if it is equal to sigma S3, then it is equal, then K is equal to 2.
Okay, so if you have too many points, so if the trajectory is like this and very many visits to zero, then this is not a problem.
I will show that this is not a problem.
Okay.
Now I want to show that K cannot be bigger than 2. But actually, these are the same considerations as with the Tanaka SD, because if we have K bigger than 2, then at times sigma 1 and sigma 2, the Brownian motion will have local extreme at the same level. It can happen that, well, it cannot happen that, let's say, the Brownian motion hits the level at time sigma and then goes below, because Brownian motion doesn't have points of decrease or increase. So at times
You mean fixed point, fixed non-random point?
No.
It's stopping time.
At any point, at any point.
No, there are local maximum of Brownian motion, but they are
Yes,
not.
But there are no points of increase.
Yeah, this is true.
The probability that there exists a point T such that for some epsilon, let's say maximum of B on T minus epsilon T is equal to B of T is equal to minimum of B.
Yes, but you even don't do not need this because you have stopping time and you have strong Markov property, and we know that at fixed point we have.
Sigma is not. I'm not sure the sigma is a stopping time for B.
But at least this is
Maybe.
the first visit after something, yeah.
So any case, we cannot have two local extreme at the same level. So K cannot be bigger than 2. But okay, and when K is 0, if the point S0 is equal to S phi n of S, then we have no problems. If not, assume that theta is approximated from above by functions phi and j. And then I need to apply the theorem from by Birdie and Caspi that theta will be equal to it will solve the same as D. Moreover, they showed that if local time at 0 is bigger than 1, then it will coincide after time t with some function phi n. Hence, in this case, we also get a strong measurable continuous modification of the flow.
Georgii and Barzi and Caspi proved that there are triple points and lenses.
Yes.
So does it not contradict your result?
No, because here we choose some functions from this flow. Yes.
Okay. Thanks.
So it does not, because when we hit, so when we leave 0 and then we hit it, yes, then we change the function. Okay, so this is what I wanted to present. Thank you.
Okay, thank you for interesting talk. And maybe somebody have questions or comments, please. Maybe I have a question related to Tanaka equation and then to this situation, because in this case, one can consider maybe measurability solution too, and then discuss the flow in the space, the measurability flow. So do you have the feeling that if you can have such a good strong flow modification, then for measurable flow you can also construct the good modification?
I hope yes.
Also, maybe we discussed this question before. It will be interesting to understand the structure of this bifurcation point and the noise related to its structure, like Cerielson did for zeros of Brownian motion for Tanaka equation.
Yeah? Yes, but I didn't look at it.
So you actually, this is a question about exams. Do you have some exams when this set is of complicated structure relatively to space also and time, not only located on the fixed line, on the fixed set, like in the.
I think that for even for Aratia flow it is dense.
Yes, so maybe it is good to start to find some good tools to work with it, to locate it, to say something about its structure, to study noise related to it, and so on.
Yes. Well, actually, we wanted to remove the set F from our construction.
Yeah,
but we didn't remove.
But maybe it can be checked that you can just find some sequence of good sets, not closed, but good sets, which gives in the intersection this one. Yeah. By the way, let me ask you, if you have a not closed set, but such set that you will have a good stopping times when you hit it, yeah, it can be not only closed set. Yes, then
yes.
all construction maybe remains the same or not?
Well, this looks like a potential theory for Markov processes. When you consider hitting times of some
yes
not closed sets. We had such ideas, but now F is a closed set.
At least now. Yeah. Okay. Okay. Thank you. Thank you again for interesting talk. And maybe you know who will be the next speaker.
It will be FanView 1.
Mhm. Okay, with something about equation with energy
McKean-Vlasov
equation is
McKean-Vlasov equation.
okay, and energy.
Yes.
Okay, thanks everybody, and see you next week. Bye.
Thank you. Thank you.
Goodbye.
Bye.
Thank you.